Hello and welcome. This is part 2 of my video lecture on chapter 4. I'm going to describe how you can apply what you learned in part 1, specifically what you've learned about the central limit theorem and standard error of the mean, how you could use that information to find statistical evidence, specifically p-values and confidence intervals. We're going to be using p-values and confidence intervals for the rest of the semester, so you might as well learn it sooner rather than later. As a brief review of what we talked about in part 1, you learned about the central limit theorem, and you learned specifically that the central limit theorem tells you specific things about the shape of a distribution of sample means. Now, let's remind ourselves what a distribution of sample means is. A distribution of sample means is really a population of means. It is the distribution of all possible means, i.e. the population of means. It's all possible means you could get of a specific size. You can compute certain things about the distribution of sample means. For example, something called the standard error of the mean. That is a measure of sampling error. And we're going to use this information, again, to compute p-values and confidence intervals. Another bit of information that's really important that you know, I didn't cover this as explicitly as I maybe could have in part 1, is this 68, 95, 99 rule. Specifically, approximately 68% of all scores, of all sample means, I should say, 68% of all sample means are going to fall within one SEM step above and one SEM step below the population mean. Again, how big is an SEM step? Right here, the standard deviation of the population divided by the square root of 1. It's kind of like a z-score, really. But it's one SEM step up and one SEM step down. In the distribution of sample means, those two scores bracket the middle 68% of all possible sample means. So that's good because most sample means are going to end up being quote close to the population mean. And again, if you come out here to 2 SEM steps above and below, a little more than 95% of all possible sample means are going to be within 2 SEM steps above and 2 SEM steps below the population mean. Okay, so now let's go ahead and jump into this part, which is on this is just how you can use this information to get statistical evidence. So we're going to talk about 2 different types of statistical evidence. And again, we're going to use these 2 types of statistical evidence for the rest of the semester. The first one is a p-value. P stands for probability. So specifically, you're going to get a lot of different types of p-values, but in general, a p-value is the probability of getting a given result, and I'm going to use an example of getting a specific z-score, but we'll use different examples later in the semester. So it's the probability of getting a specific z-score assuming certain assumptions. And again, I'm going to show you an example. The other type of evidence I'm going to talk about are confidence intervals, and confidence intervals are a range of plausible values for population parameters. It is important that you know these definitions, so write them down, commit them to memory. It will help you if you do so. Okay, so now an example on p-values. Here's the research situation. Suppose you've got a professor who has taught a given class many times, but every time that professor has taught the class, it's been a face-to-face class. That's what that FTF is, face-to-face class, so an in-person class. And this professor always took satisfaction scores. How satisfied were students about that course after they took the course? So you might consider this the population. Every student this professor has ever taught in this given class. And the average satisfaction score of all the students was 4.4 on a 5-point scale. And the standard deviation was 1.7. Now, COVID happens. The professor had to teach the class online now. And the professor is interested in knowing, gee, do online students like the class better or worse or what? So he takes the sample of his students for the given class that just completed the online class, and their mean satisfaction score was 4.5. This is considered just a sample because it's just one class, right? So it's 4.5 on a 5-point scale. Now, obviously, the 4.5 is higher than the 4.4. So we know that the sample of online students have a higher score than the population of face-to-face students. But because of sampling error, we don't really know. Maybe this sample of students were just crazy good. Who knows? Maybe that sample of online students doesn't represent the population of online students really well. So what we're really interested in here is this research question up here. What's the probability, the p-value, what's the probability that the difference in student satisfaction scores between the online students and the face-to-face students, what's the probability that that difference was created by sampling error? So again, the difference here is 0.1. This group was about was exactly 0.1 more satisfied. Is that difference of 0.1 due to sampling error? What's the probability that that difference was created due to sampling error? That's our research question. So this is the same situation. And what we're going to do here is we're going to answer that research question by using the z-score computation that you already know with a slight modification. So here is the research situation described in words. We've got an online class with 30 kids in it. Their mean satisfaction score is 4.5. And I want to compare that sample of scores to the population of students of every other student who's ever taken that class before. And there's their parameters, 4.4 and 1.7. And then this is the research question just worded slightly differently. What we need to do now is compute the z-score. What we do is we find the deviation score, the difference between the mean, the sample mean and the population mean, so 4.5 minus 4.4, and then we divide that by sampling error. So how far apart was the sample mean and the population mean? How far was that? And then we're going to divide that by the typical amount of sampling error. And that's what the SEM is. It's the average or typical amount that any given sample mean of that size we would expect to deviate from the population. So if we compute this number, we're going to get this z-score here. This z-score of 0.322, of course, has a p-value associated with it. And we need to find that by using Appendix A. So we can do that pretty straightforwardly, just like we've always done. We draw our little curve, make sure we center a z-score of 0 under the peak, and then we can go plus 1, 2, 3 on the left, or excuse me, on the right, and plus or minus -1, -2, -3 on the left. Locate where 0.322 is. This is our z-score, 0.32. Then if you look up in Appendix A, a z-score of 0.32, and then look in the tail, because that's what this is, a tail, you will find that the p-value for a z-score of 0.32 is 0.37. This is the proportion of of all sample means that are equal to or greater than a z-score of 0.322. Okay, so again, this is the proportion of all sample means that are equal to the sample mean we got or greater. Okay? All right. Now, how do we interpret this value? So here's our p-value again. And the sort of wordy way of interpreting this, the precise way, this is the probability of sampling 30 students. That's what we got right here, 30 students over here. It's the probability of getting 30 students with a sample mean of 4.5 or higher. And another way of saying that, it's the probability of getting a z-score of 0.32 or higher. That probability is 0.37. So basically, about a third of the time, you would get this result simply due to sampling error. About a third of the time, you would get this result simply due to sampling error. That's a pretty high probability. That's a pretty high possibility that it would be due to sampling error. Okay? Oops. And since that's such a high probability, you would come down and make this conclusion. There's really no compelling evidence that the population of online students have a higher satisfaction score than the face-to-face students. Because this difference of 0.1 between these two means, that difference about a third of the time would happen due to sampling error. So that's not very compelling evidence. Compelling evidence would be a very small or very low p-value. If you get a very low p-value, that would be compelling evidence that the result you got probably did not occur due to sampling error. Here, we don't have that. We have a pretty high p-value. So it seems likely that this could well be due to sampling error. The next kind of statistical evidence I want to show you both how to compute and interpret is the confidence interval. It's still based on the standard error of the mean. The standard error of the mean still means the same thing. It's still the typical distance of all possible sample means from the population mean. And it's still going to be based highly on the distribution of sample means and specifically this rule that 95% of all possible sample means are going to be between 2 SEM steps above the mean and 2 SEM steps below the mean. We're going to kind of use the knowledge of that to compute a confidence interval. So we still have the same population of face-to-face students and the same sample of online students. But here our research question is slightly different. Here we want to know what are the plausible values, what are the range of plausible values for the difference in satisfaction scores between face-to-face students and online students. Now we know the mean difference between the sample and the population here is 0.1. But again, this sample might not be a perfect representation of the population of online students. So we need to have some margin of error. We need to find out how far off this sample could plausibly be. If it doesn't represent the population perfectly, which is likely, it probably doesn't represent it perfectly, well, what's the range of plausible values for this mean difference? We hope it's 0.1, but again, if the sample doesn't represent the population perfectly, it might be quite a bit higher than 0.1, quite a bit lower than 0.1. So we need to compute a confidence interval to figure out what's the plausible range that the mean difference between this population of online students and this population of face-to-face students. How big might that difference be given the sampling error that we expect? So we're going to compute that now. Well, we start off with what's known as a point estimate. The point estimate is simply the mean difference between the sample mean and the population mean. So again, we've talked about it several times, that difference is 0.1. If the sample represents the population perfectly, then we would have the statement online students are 0.1 higher in their satisfaction than face-to-face students. But we don't know that that is exactly the case. We don't know that the sample represents the population perfectly, so we got to have a margin of error. This is going to be our starting point, but we're going to add a margin of error to that. How do we do that? Well, we're specifically going to add a 95% margin of error. Well, it makes sense that sampling error is going to be included into this margin of error, the MOE, and that's what it is. Again, it's the standard deviation of the population divided by the square root of n, so we're going to compute that. But we can't just leave it at that. If we just left it at this SEM, we would have a 68% margin of error, because it would only include the range between a positive 1 and a negative 1. So we want to expand that a bit to include the middle 95% of scores. We want to have a 95% confidence interval, not a 68% confidence interval. We do that by multiplying 1.96 times the expected sampling error to get our margin of error. And we do that, we get a margin of error of plus or minus 0.68. Now, what do we do with that? Well, we add that margin of error to the point estimate to get the upper bound. This is the highest plausible value for the mean difference between the two populations. And in that case, it would mean that online students are more satisfied by about 0.7. We also have to compute a lower bound. That lower bound, we simply take the point estimate, 0.1, and we subtract from that the margin of error of 0.6, and we get negative 0.508. So those two values, positive 0.7 and negative 0.5, those are the upper bound and lower bound, respectively, for the confidence interval. Those are every value, both of those values and every value between those values are considered plausible values for the mean difference between the two populations. The upper bound suggests that the online students are more satisfied by about 0.7. The lower bound suggests that the online students are less satisfied by about 0.5. When you're interpreting these confidence intervals, there's a few things to keep in mind. First, you have to remember that the point estimate, the upper bound, and the lower bound are all estimates. They're based on a sample, and that sample might not represent the population perfectly, so that means this point estimate might not be right. Well, that point estimate is the base on which we base the upper and lower bounds. So you have to remember that that point estimate isn't set in stone. If you did the study again, you might have a different point estimate. So that means you would have different upper bounds and lower bounds. Always remember that confidence intervals are estimates. Now, if you have a big sample size, they're probably pretty good estimates, but they're still estimates. The other thing to keep in mind when you're interpreting confidence intervals is that values in the middle of the confidence interval range, again, the range is from positive 0.7 to negative 0.5. Everything between that's plausible, but values in the middle of that range, values close to the point estimate, are considered more plausible. So if you had to make a guess at one value, what's your best guess at what the difference between the two populations is, it would be the point estimate, 0.1. That's your best guess. As you move away from the point estimate, those values become less probable, less plausible. Another thing to keep in mind is very wide confidence intervals mean that you shouldn't be extremely confident when you interpret your results. Look at this, right? There's a very wide range. The upper bound tells you that the online students might be 0.7 more satisfied. The lower bound tells you something almost the opposite, that they would be 0.5 less satisfied. So if all of those and everything between those is plausible, you shouldn't be overly confident in your results. All right, that's probably enough for now. There is something else that is covered in the text, but I'm not going to cover it in this video because we're going to cover this a lot more in chapter 5. It's simply that you can also compute confidence intervals when you do not know the population standard deviation, and instead you would just use the sample standard deviation. But again, like I said, we're going to cover that in more detail in chapter 5. There are some important differences, and we'll cover them next time.